Another 7-minute summary for you guys here today. Last video we looked at chapter 40. Today we're looking at quantum mechanics, chapter 41. Crazy subject. We got a couple sections over here. The wave function, section 1. Analysis model, quantum particle under boundary conditions. The Schrodinger equation, a particle in a well of finite height, tunneling through a potential energy barrier. Applications of tunneling, the simple harmonic oscillator. Oof, okay. As you see in these 7-minute summaries, I just read a couple sentences. I just look at some pictures. I try to look at bolded words. I try to look at some graphs, I don't know, some equations. I try to just get the broad picture of what this chapter is about. Then I can go in and fill up some kind of unknowns. But you really want to start off with this broad picture. Maybe take a look at each of these sections, write down the name of the section, the wave function, and then write down like 4 or 5 notes for each of these sections. If you have that and you can define each word, like for example, the Schrodinger equation over here, maybe it's the first time you're seeing that. Maybe it's not the first time because it's a pretty popular equation. But this, tunneling through a potential energy barrier. So potential energy you may have seen before, potential energy barrier, what is that? Tunneling, you can see tunneling, they actually talk about it a couple times here, tunneling over here. Just try to get the broad strokes of the chapter and see if you can remember those things just by talking about them and seeing them a couple times here and there. They will be very helpful once you go into the homework or an exam to start solving problems. So today, I don't know anything about this chapter. I'm gonna set a timer for 7 minutes. Take a sip.
All right, 7 minutes, starting now.
Thank you, madam. Let's get to work. In this chapter, we introduce quantum mechanics, an extremely successful theory for explaining the behavior of macroscopic particles. In this theory developed in the 1920s by Erwin Schrödinger, Werner Heisenberg, and others, enables us to understand a host of phenomena involving atoms, molecules, nuclei, and solids. All right, let's check at 41.1, the wave function. In chapter 40, we introduce some new and strange ideas. All right, I'm going to leave it at that. Let's take a look at this equation here. Probability divided by V. This symbol in the middle, this tiny symbol right here, I'm trying to select it, but I can't. This little tiny symbol right there means proportional to. So what does that mean? We're talking about probability. We're talking about the wave function. What does this mean? Let's keep looking down here. Okay. We got the word probability amplitude or the wave function. And then they also show you this symbol, the Greek letter for psi, I believe. So we got an interesting looking equation here. This looks crazy. What is this talking about? Space and time dependent wave function psi, the Greek letter psi there. Okay, they are kind of introducing some crazy stuff here, but probability density, like absolute value bars, psi squared. And then we got the probability density over here. Let's take a look at the pitfall prevention. The wave function belongs to a system. The common language in quantum mechanics is to associate a wave function with a particle. The wave function, however, is determined to be the particle and its interaction with its environment. So it more rightfully belongs to a system. In many cases, the particle is the only part of the system that experiences a change, which is why the common language has developed. You will see examples in the future in which it is more proper to think of the system wave function rather than a particle wave function. Okay, this wave function, I guess, describes a system or a particle. All right, and there is some probability kind of associated stuff here. We haven't seen anything about probability in this entire course, so it's kind of a new type of mathematics that we're looking at. We can read a little bit about this later, but let's take a look at this equation here. Wave function for a free particle, and then we have here e to the power of I kx. We have a definition for k over here. I'm not going to get too deep into those weeds yet. One-dimensional wave function and expectation values. Okay, this is a word we're going to see quite a lot, expectation values. Probabilistically speaking, like in a probability course, you may see that. You may see a function like this also. Don't be too worried about this integral. We're not going to do any crazy integrals here. It's just important to know that we're talking about probability here. And then you could see this graph over here. The probability of a particle being in the interval a less than or equal to x less than or equal to b is the area under the probability density curve from a to b. So this is why we bring into play some integrals. Integrals are a very good way of calculating areas under curves. And turns out the wave function gives you some kind of probability of finding the particle somewhere or some information about the system. We got normalization condition of psi, another crazy looking integral equation. Don't worry about that too much. Maybe search up some stuff like normalization condition probability. Take a look at this word normalize. Take a look at this word expectation value. We're going to slowly learn about them soon. Let me check the timer here. We got 3 minutes, 17 seconds. Okay, a wave function for a particle, example 41.1. You're going to see that doing these examples in this chapter specifically is going to be immensely helpful. Look at this crazy math here. Right now, I'm not going to look at it too much, but just know that these are here and they're here to help you. They give you a whole solution, right? Analysis model, quantum particle under boundary conditions. Particle in a box. Interesting. We got some graphs over here. This figure is a pictorial representation showing a particle of mass m and speed u bouncing between two impenetrable walls separated by a distance L. This figure is a graphical representation showing the potential energy of a particle box system. The blue areas are classically forbidden. Interesting. What is that talking about? What are these little functions here? Not sure. Don't have time to look at them. But I'm going to just keep in mind this wave function is like the focus of the chapter, or like the chapter so far. We're going to keep going. Ooh, some nice looking, these almost look like they're not exactly standing waves. I mean, maybe these ones here are standing waves, but this reminds me of like when you look at a guitar, you pluck a string, the strings do something like this. And we have some kind of function here. I'm assuming this function describes all of the little waves that we see in these pictures up here. Normalizes wave function of a particle in a box. Pretty interesting. We got another interesting equation, quantized energies for a particle in a box. Cool. Don't worry about how complex these equations look. We're going to be chilling. We're going to keep pushing through microscopic and macroscopic particles in boxes. Cool. Some example, expectation values for the particle in a box. All right. Boundary conditions on particles in general. And we have two little orange bullet points here. And we have a couple more, few more bullet points here. I'm going to keep that in mind. And then here it says in general, and it gives you a big orange box. I'm not going to read that. I'll just go back to it later after the 7-minute summary. Let me take a sip of tea, actually. Some mint tea. Let me check the timer. 1 minute. The Schrodinger equation. Whoa, this looks crazy. Time independent Schrodinger equation. This looks wild, but I'm assuming it's important. Erwin Schrodinger is put over here. Let's take a look. Erwin Schrodinger is best known as one of the creators of quantum mechanics. Pretty fitting to put him in this chapter. His approach to quantum mechanics was demonstrated to be mathematically equivalent to the more abstract matrix mechanics developed by Heisenberg. Schrodinger also produced important papers in the fields of statistical mechanics, color vision, and general relativity. All right, crazy dude. We got the word time-independent Schrodinger equation over here. Looks interesting. We got a couple more bullet points here, but since I have 17 seconds, I'm going to push through. Particle in a box revisited. A particle in a well of finite height. Oh my god, I don't have time to finish this. Tunneling through a potential energy barrier. Applications of tunneling. Nuclear fusion, scanning tunneling microscopes, and resonant tunneling devices. And that is my timer. I don't know if you guys can hear it, but it went off. Let's zoom through. Damn, we missed a whole section, the simple harmonic oscillator. Okay, that was actually a very bad 7-minute summary, guys. Sorry I missed out on all of those things. Let's take a look at the definitions and concepts and principles here. Maybe it'll kind of solidify the chapter for us. So we have the wave function psi for a system. It's a mathematical function that can be written as a product of a space function for one particle of the system and a complex time function. And they show you the entire graph of the thing, or the entire function over here. This looks kind of weird. Why is there so many dots here? I have not seen a function like this before. This is strange. And they give you some definitions like this. Omega is equal to 2 pi f, the frequency, angular frequency of a wave function, and I is equal square root minus 1. So this I is the imaginary number. Normally, if you plug in square root of negative numbers in your calculator, it gives you an error. Imaginary numbers are ways of like going around that, and it turns out to be very helpful in lots of mathematics. So you can see that I right over here. You can actually see this also if you take a look at Euler's identity. Some people call this the most beautiful mathematical equation ever. It's used in pretty much every, where is it used? I mean, quantum mechanics for sure uses it. I think you use it in kind of computer design if you want to spin and rotate shit. I don't know too much, but we will take a look at some of the other sections here. Don't worry if this equation looks kind of scary to you. This is the first time you guys are seeing this maybe. So don't stress. Just look at it and be like, wow, that's cool. And then, you might get more comfortable with it in the homework. Let's take a look at this. The measured position x of a particle averaged over many trials is called the expectation value. Remember how I told you this word was important? Here it's bolded, and here they give you an equation which is literally defined as the expectation value. So if you search up expectation value, you might see something like this. Like I said, this is a statistical physics or just statistics kind of concept. But it turns out to be very important in quantum mechanics. That's why they use it here. So sometimes in statistics, they might replace this psi with another function, f, and the expectation value here, x, is the same. Turns out it's important. We'll take a look at that more, but let's take a look here. So in quantum mechanics, a particle in a system can be represented by a wave function, psi, x, y, z. Psi is a function of x, y, and z. The probability per unit volume, or probability density, that a particle will be found at a point is psi with absolute brackets squared, or psi with a little star over here and then another psi, where psi star is the complex conjugate of psi. Okay, that's crazy. No need to worry about that for now. If the particle is confined to a moving along the x-axis, the probability that it is located in the interval dx is psi squared dx. Furthermore, the sum of all these probabilities over all values x must be 1. This expression is called the normalization condition. So what this is saying is that, okay, we're measuring the probability of finding the particle or whatever quantum thing that is described by this psi. We're trying to see if we can find it over the entire x-axis. And if it exists, we have to find it, so the probability is 1. This is the normalization condition. Sometimes you see this in statistics, sometimes you don't. Maybe you can take a look at Wikipedia, normalization condition for quantum mechanics, or ChatGPT, and you can kind of find a way of explaining this to yourself. Again, don't stress. It is a complex kind of field. Right now, just know that some kind of wave function statistical thing is going on here, and we can learn more about it. If a particle of mass m is confined to moving in a one-dimensional box of length L, whose walls are impenetrable, then psi must be 0 at the walls and outside the box. The wave function for the system are given by this little sign over here. We got sign, we got n is equal to 1, 2, 3, 4, so on, where a is the maximum value of psi. The allowed states of the particle in a box have quantized energies. This. So quantized energies, this is interesting. This equation is normally very important. This can be used to find energy of some kind of, well, in this case, it's a particle in a box, but it turns out that this one-dimensional box is fairly useful for modeling atoms, electrons around an atom. And this is kind of like a simple version of modeling this. So I say simple, it might look complicated to you, but no stress. Most of the time you just use this equation here and you plug numbers in, like you plug n equals 1, 2, 3. All of these numbers here they give to you, and then you find energy of whatever you're talking about. Most of the time it's a particle in a box here, but sometimes they might change the problem a bit. So no need to worry, just remember that there's a psi over here. Psi is given by a function. There's energy. Energy is also given by a function here. And each of these have this little value n, which you can kind of increase by the integers. Let's read this last little box here. The wave function for a system must satisfy the Schrodinger equation, the time-independent Schrodinger equation for a particle confined to moving along the x-axis is, and then they give you this crazy looking equation here. It's an equation because there's an equal sign here. There's something on this side of the equal sign, and there's something on this side of the equal sign. And they tell you U is the potential energy of the system, E is the total energy. So the Schrodinger equation, in short, you can think about this kind of like the Newton's second law. This is classic like analogy that they use to explain this to people. When you learn about Newton's law in classical mechanics, which I have not done a course about yet on this channel, hopefully I'll do that sometime soon in the future. You learn about Newton's equation, you learn about forces. Let's say you're modeling some block sliding down a hill, or a ball sliding down a hill. You have forces, the force of gravity, the force of friction on the block or whatever. And then you want to find x, how the block moves as a function of time. In this case, the Schrodinger equation is kind of like Newton's equation. They give you a whole bunch of shit over here. You have the potential energy, you have the total energy of the system, whatever that is. We don't really know yet. It's just kind of general. And you plug stuff in and you can see in this equation, we actually have psi over here and over here and over here. And this psi is actually similar to this psi, similar to this psi over here. I'm trying to mark it here. And you actually found out that psi over here is a probability density. So you can use the Schrodinger equation. You can locate or calculate what psi is. If psi is given to you like this is psi for a very specific potential energy and total energy. You find a specific function psi, and this function will tell you stuff about the system. Probabilities of finding the particle here and here, energies of specific particles here and there, so on and so forth. Let's end off here by looking at the quantum particle under boundary conditions. An interaction of quantum particle with its environment represents one or more boundary conditions. If the interaction restricts the particle to a finite region of space, the energy of the system is quantized. Okay, interesting. All wave functions must satisfy the following four boundary conditions. 1, psi must remain finite as x approaches 0. 2, psi must approach 0 as x approaches... Okay, I don't want to read all these. This is crazy. I'm just going to keep in mind the main stuff here. What did we learn in this chapter? We got psi, that kind of strange looking letter over here, which looks like a little fork, or a threek, because it has 3 pins over there. So this is an important thing of the chapter. We got the Schrodinger equation, also important. We got a one-dimensional box. Let me take a sip of tea over here. And we're going to just take a look at the total pages. So this is the starting page: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 pages. And we have 2 pages of the summary here. 21 pages. As we saw, the previous section was also around 20 pages or so, this introduction. And in between, we obviously have a bunch of problems. Here's a whole bunch of problems from the previous chapter. The more problems you do, the better you'll get in this chapter. But overall, that is the 7-minute summary. I understand it is crazy stuff. You got some more chapters to look at after this. Let's take a look at the bookmark chapters. So we did a long summary of relativity, short kind of 7-minute summary of quantum physics, another short 7-minute summary of quantum mechanics. Then we got 4 more chapters over here: atomic physics, molecules and solids, applications of nuclear physics, particle physics, and cosmology. So a lot of stuff. That's why it's super important to spend as much time as possible doing those 7-minute summaries, doing longer summaries, doing some problems, reading, check some history, check whatever you need help with. Drop some questions or comments down below. I will be happy to discuss with you guys about the intricacies of these subjects. And I hope you enjoyed today's video. I'll see you guys later. Hopefully we can solve some problems together on this channel. Thank you as always for watching. Peace out.